Okay, so now we can begin the real summit with our first keynote talk, and I'm delighted to introduce Martin Casado, who is going to be our first keynote speaker. In one line, if I have to introduce Martin, I would say he's the person why we are here. He's the person who put us on this OpenFlow and software-defined track maybe 4 years ago or earlier. Martin completed his PhD in 2007 at Stanford University, and his PhD was about security management in enterprise networks. As part of his thesis, he explored ideas such as separation of data and control, logically centralizing control for doing security management, and then he implemented a particular architecture, deployed it at Stanford. After finishing his graduate work, he continued working in this area. He contributed to OpenFlow specification. He contributed to development of NOx, which is the network operating system that is popularly used, NOx applications, and so on. And these open source tools have been very, very instrumental in enabling other people to explore potential and demonstrate the potential of OpenFlow and software-defined networking. As a result, we now have Open Networking Foundation, as Dan mentioned. It has 40 plus companies. Oh my God, this is running. I don't know what's happening. It's running by itself. So please be patient with me. So there are now, oh my God, I don't know what I can. I think I know what's happening. Okay, but I don't know how to turn it on. I have my, oops. I had rehearsed my stuff, and that is what is playing. Okay, so we know that has led to ONF with 40 companies that are introducing products and so on. There are 200 plus deployments around the country, around the world, and Open Networking Summit. And by the way, he's also co-founder of Nicira, but it happens to be in a stealth mode, so we will leave it at that for now. But I think at the end you will agree that Martin and his thesis has contributed already to the field of networking, and it has been an extraordinary contribution. But Martin is no ordinary person. When we look at what he does beyond OpenFlow, SDN, and trying to make Nicira successful, he does race, he runs and does races, and you can see the kind of races he participates in. So he's a phenomenal guy. I don't know how he manages to do all this, but he's able to make it happen. Okay, so we are delighted to have Martin. He's passionate, he's creative, and he's very ambitious to have an impact. And when those three things come together in an individual, you know those individuals make a huge difference to the state of world. So with that, I will have Martin. And Martin is going to talk about origins of OpenFlow and SDN.
So while he's doing this, I'm going to go ahead and kind of introduce what I'm going to talk about. And as we all know, there's been a tremendous amount of press on OpenFlow and SDN in the last 3 or 4 years. And periodically I'm on the other end of that phone, kind of answering questions about it. And as part of that, I've realized that there's an awful lot of redundancy and sometimes confusion on the questions that get asked. And so the goal of this talk is to kind of provide some context. On OpenFlow, answer some of these questions, and to kind of do it in the form of a historical narrative. So what I'm going to do is I'm going to talk about some of the early work that led to OpenFlow, kind of some of the thought process that went into it, and then some of the major drivers that kind of moved along the evolution of it. Then I'm going to address some of the more pervasive questions directly. Like, here's a question people ask, here's why it's wrong, here's why it's right. And then finally, I would like to take all of this and get a little bit reflective about why OpenFlow has been so successful. What about it has made us so successful, and what we can do not to lose that, so we continue to be successful in the future. So that in a nutshell, will be my talk. before I get to any of this, I want to make the point that something like OpenFlow does not happen in isolation. The point of the slide isn't the people that are on the slide. I'm sure I've missed more than half. The point is that there's been dozens of individuals that have contributed from dozens of organizations. And I truly believe, and I'll talk about this later, that our biggest asset is the community around us. And it's because of that we're successful. Okay, so I'm going to start with a story. So back in 2002, 2003, post 9/11, I used to work for the feds. And I worked in the intelligence sector. And the team I worked with, we were responsible for auditing and securing some of the most sensitive networks in the United States. And this is pretty serious stuff. Like literally these guys got broken into, people died, very literally, right? And so we took our job pretty seriously. And the mandate was actually fairly simple, which is, okay, I have a network. I want you to go look at the network, enforce some policy. I'll tell you what that policy is. But I also want you to make sure that that network, while it's under duress, while things are moving around, continues to function as well, right? So I want availability. I want to be able to ensure that the mission continues to go forward. But I also want you to be able to enforce some security policy that's been specified. And it was really shocking to me at the time to realize how difficult this was to do. Now, I don't remember all of the contortions that we went to, but I'm going to kind of try and give you a flavor. One problem is okay, so I've got some network. There's my switches, my routers, and my hosts, and we have this constant conflict between the need to put policy places and then make sure the routing protocols wouldn't route around them, right? So I'd have, you'd have some policy, and because you wanted to keep availability, you wanted to make sure this policy was replicated at different points in the network. Right? Now, you can do this by hand, which is probably not a great idea, or you can use this kind of more in a template way. But the problem with the template is it assumed that the topology looked a certain way. So now you start constraining the topology. For example, we needed to have a symmetric topology because this is the way that the policy files would actually work. And we started having a kind of a heterogeneous topology where you'd have kind of different policy requirements for the access than you have with the edge, right? So you can't kind of interpose or change any of these components. In addition, adding or moving a machine was like an act of aggression. I mean, literally, I think in one network we had to update 8 points of state anytime that we added or moved a machine, whether that was port security or policy routing or ACLs or VLANs or whatever it is. And having come from somewhat of a networking background, I had a very difficult reconciling these networks that we created with the networks I've learned about as an undergraduate, right? So if you take an introductory networking book and you open it up, networks are touted as scalable and robust, and they can handle change very easily. I mean, these are the networks we learn about, right? And we would end up creating something that was very different. For example, we would limit redundancy on purpose so that we would have choke points to ensure security policy, because there's a trade-off between human error and availability. We had constrained the topology, because that was the only way we could actually automate the placement of these things. We had very poor response to dynamic events, right? I mean, literally moving a machine would take hours, right? Now, routing protocols, very quick. Human beings, not so much. And finally, I mean, the scale of the systems that we're creating were totally limited by our ability to manage the state within them. So at this point, it's totally reasonable to ask the question, okay, Martine, I know that you did this was 10 years ago. A, maybe you're an idiot, you don't know how to manage these things. I think that's a totally reasonable thing to ask. Maybe your Cisco sales rep didn't know what devices that you should be using, which is reasonable. But I kept thinking about it, and the team did as well. And I believe then, and I believe now, that this property is actually intrinsic to the way that networks have evolved. And so I'd like to talk about that very briefly. So here's my idealized pipeline of a switch. So if you got a switch and you kind of pop the top and you look at what happens, you have packets that come in, they get thrown against a set of tables. Those tables determine what happens to the packet. Does it get dropped? Does it get forwarded? Does it get replicated? And then they pop out the other end. That is networking. That is actually all of networking. Is that problem. Now these tables are populated in one of two ways. Some tables are populated using dynamic routing algorithms, right? This is like the L3 table and the L2 table. So a distributed dynamic routing algorithm is something that runs on every single node, and anytime there's a change, it'll kind of communicate with everybody else, it'll calculate some state, and it'll throw it down into a table. And if this was all that networking was, If the entirety of networking was forwarding, we'd have all the properties we like, learn to love as kids, right? It'd be scalable, it'd handle dynamic motion, you could handle redundant paths, you'd have high availability, that's great. But there's this whole other set of state that you have to figure out how to manage. So, to some first order of approximation, every packet, most packets touch all of these tables. And the other tables are actually the tables that we use to add our own kind of secret sauce, our own magic to the network. Things like policy routing, things like ACLs, things like tagging. And these tables, unlike the forwarding tables, are populated through very different mechanisms. Human beings, maybe scripts. So I've got 3 things to say about that. First, humans really suck at state management, right? Routing algorithms are great at it, they compute it really quickly. Human beings, we're slow, we're error prone, we can be malicious, we can be hit by bans. This is just not something that we're good at, right? So you take a network, I pull a link, it converges really quickly, that's great, you got the smart routing algorithm, you got some human being whose beeper goes out that's got to go kind of fix things up. And clearly we have a mismatch. But let's assume that, okay, we know humans are poor at this, why don't we have a program do it? So we started looking at switches, and there's actually really no well-defined APIs at the time, and this has changed, for data path management. Right? So if you wanted to program it, there are really no well-defined APIs to do this. Now, there were management APIs, they've been around for a while, there are even SDKs that you could get. But none of them were focused on the problem of consistent state management. Right? But even if you did have one of these, and this was kind of really the kicker for me, if you do have an API and it's like OpenFlow and it's sitting on the switch, it still wasn't clear what sort of algorithm that you'd use to distribute the state in the correct way. So, for example, for me, the ideal secure network has a very high-level policy language, and it's totally decoupled from the underlying, totally decoupled. So you declare something at a very, very high level, and it gets enforced throughout the network. That, to me, is like eating. If you look at this problem, you look at the policy languages that you want to use, they're normally something like data log, right? So now, in order to build a network that listens to, that is run by this language, you end up having to build a data log compiler. I mean, that's what these things do. So I have to figure out how to build a data log compiler in a purely distributed way if I want to run it on an architecture like this, right? So it wasn't clear for all of this other state in the network how you would actually do the state distribution in the way that is normally been done. So that's the problem. So at this point, I kind of leave the government. I head over to Stanford. I'm very lucky to work with Nick and Scott. And we focused pretty much on this problem. And the high-level problem that we ended up looking at after a bit of grad student meandering was simple. Okay, so say you wanted to program a network. How would you do it? And in the context of everything that I just told you, it actually boils down to, okay, so how do you programmatically manage all the data path state in the network? I mean, this is the problem we wanted to solve, because if that happens, then I can write whatever program I want, get it to do it in the way that I wanted to do. I've been in a place in industry, in the Fed space, where I wanted to do this, and we've been unable to. Right? So now I'm going to try and kind of summarize 4 years of research in about 6 slides, so you're just going to have to bear with me. And I'm going to skip a bunch of intermediate states. But we kind of came up with two conclusions. The first conclusion is, if you grab the switch off the shelf, and you take a look at it, and you pop the top, you get the data path like I talked to you before. And there were 2 things about that made it difficult for us. Now, we were in academia, we could do pure research at the time, and so we were a little bit idealistic about this. So the first problem we had is, networks had not been evolved to be programmed, at least the standard forwarding chips. So a lot of the algorithms that are commonly used, like L2 and L3, were totally fixed in hardware, which is fine, but what if I didn't want to use that, right? And that would be problematic. So you had a lot of fixed functions in these switching chips, and what we wanted to do is create a general programming environment. Another problem is often the nuts and bolts of the hardware chips are actually exposed through any interface that we can get to program them, right? If we go like Broadcom, get an SDK. I mean, a lot about what the chipset looks like you can actually see within the development environment. And the final thing is, as far as we could tell, none of the APIs that you could use these actually had clear state consistency semantics. If you look at what this problem is I want to write a program that manages some state somewhere. I need things like transactional guarantees. I need to know what happens when I write to state. I need to know what the failure modes are. If I do that, or if I don't have those, there's no way I can have a consistent knowledge of what's going on in this, on this switch. So the first thing that we propose is, okay, we're just going to generalize the data path. We're going to say the tables that we normally get all our flexibility are the flow tables that are in switches today. So we're going to try and avoid the fixed function tables. We're going to use the more flexible tables. And then we're going to provide an API that's minimal. And the point of the OpenFlow API, to be very clear, was to have consistent data semantics, meaning I need to know what it means to update state and for state to change. Because if that happens, then I can remotely manage that state in a way that I know what it looks like. Okay, so that was kind of step one. Step one, we're going to generalize the boarding path. Step two. So I actually have a background in distributed systems. So that's kind of where I cut my teeth, was in computational physics. And the problem with distributed systems is, like, distributing is hard. I mean, it's really hard. So to take a program and to distribute it to run on multiple systems is very difficult. And networking is actually an extreme case of that. So if I were to write an algorithm for a network, not only does it have to be distributed, it's got to be distributed to every element on the network. It's got to handle heterogeneous runtime environments, right? Lots of memory, a little bit of memory, high compute, a little bit of compute. Not only that, if you don't assume a tight coupling, whatever algorithm I end up implementing, if it's got a lot of shared state, you're going to have way too much communication. So you have to have an algorithm that actually works well in a loosely coupled environment. I mean, these are the laws of physics in building traditional networks. So, I mean, I wanted to write a policy compiler. I wanted to write a data log compiler like this really difficult NP-complete problem. And there are known ways to distribute it, but not totally distribute it. I mean, that would actually be, I actually don't think it's possible to do it in the way that would be performant. And so the second step, the first step we generalized the data path. The second step was just simply to decouple the software control distribution model from the topology. So we hear the term centralization thrown around a lot and logically centralized, but I'd like to encourage you to think about this a little bit differently. What OpenFlow and SDN does, it allows you to decouple the distribution model of your control logic from the physical topology. And that control distribution model can be anything you want. It can be purely distributed if you want. That's fine. I think that's hard to program to, but it's totally fine. It can be totally centralized if you want. Or it can be something in between. And when we know from industry, if you look at, say, how Google or Amazon or Yahoo build data centers, I mean, they use tightly coupled distributed systems that handle hundreds of thousands of servers and petabytes of data, and it scales just fine. So the point of this is not to say, oh, we're going to somehow limit the scalability. It's to say, I want to constrain my development model so I can develop new types of functions without actually having to solve the more difficult problem of doing pure distribution in a heterogeneous environment that's loosely coupled. Is that clear? And so we kind of came up with this totally, like if you looked at it, give it to a system programmer, this totally kind of humdrum simple thing, right? You've got generalized hardware. You got some hardware abstraction layer that says, okay, well here's kind of a higher level interface to this hardware. You decouple the control logic so you can have whatever distribution paradigm you want, and then you've got a control application. And I know you guys are totally familiar with this slide, but I wanted to put it in the context of what it arose. Right? And there's two problems we were interested in. The problem was here to generalize this and to decouple that. That's it. And it was on top of this that kind of I built a policy compiler, and this was it was a full data log compiler that would take a very high-level language that could operate on anything in the network, and it would turn it into state at the bottom of the network, and it would operate totally in real time. And that was the ethane project. Oops. By the way, could you pause? Yeah. Okay. So anyway, before there was OpenFlow, we had a hard time getting switches, so we'd actually run to fries, and we'd buy like whatever cheap servers there were. So this is actually one of the early ethane prototypes. And so we had like 4-port NICs and their switches. This was actually over in Gates 353. And so this was deployed throughout the Gates building and the Packard building under people's desks in the first ethane network. And it was pretty clear at this point, like, hey, regardless of what people tell you, routing in x86 is actually really slow. It's error prone, it requires a lot of power. So this is what we wanted to standardize in switching hardware so that you can actually have those switching platforms to do the type of research that we wanted to do. This literally was this is the progenitor of OpenFlow with a bunch of x86 boxes sitting around in people's offices.
Sorry.
From there, and Scott's going to talk about this more, it was very obvious to come up with the idea of a network operating system. So once you have this, you write a control application that it kind of captures the imagination. Like we wanted to immediately apply it to operations management in the enterprise, we wanted to apply it to wireless, we wanted to apply it to virtual networking, you wanted to apply it to a bunch of different areas. And once you do that, you realize that there's a lot of common functions that are used across all of them. And so, there's a very natural evolution of this, and where you create something like a network operating system, which provides the basic functions, like maybe a basic distribution harness, basic graph algorithms, basic resource management, and then you run your application on top of that. And a lot of this was done by about 2007. This led to the Knox paper, and then so I'd like to step back and just provide kind of, again, reiterate kind of where OpenFlow and SDN fall in this picture. So where is OpenFlow? There's OpenFlow. OpenFlow is a interface to the switch. And in a fully built system, it's of very little consequence. Right? If you changed it, nothing would know. Right? Because it's fully abstracted below and it's fully abstracted above. Now, I think it's a good piece to use. I think it provides the right data semantics. I think it's a standard. And I think all those things are really, really important. But this is where it fits. What is SDN? SDN, again, I mean, you guys know this. I just, again, want to put it in the context of what I'm describing. SDN says two things. It says, one, that the distribution model of the topology is not suitable for all things that you want to do with a network. It's not. I mean, there's a lot of algorithmic stuff that you want to do that you can't really do in a distributed way that scales. It's very difficult to do that. Okay, so I'm going to go ahead and now answer some of the very commonly asked questions that I've gotten in the past about OpenFlow SDN. So the first one, and I get asked this a lot, is what is the primary value proposition? This is probably the first question I get for something like OpenFlow or SDN. And we've said it, and I think maybe people have a tough time believing it. I mean, the real value proposition is the ability for people to innovate in their infrastructure. I mean, that's the primary value proposition. There are a lot of companies, there's a lot of operations out here that are interested in doing different things in their infrastructure for business purposes, for operational purposes, for competitive purposes. I mean, I think when we started this, I used to hear all the time, well, only Google's interested in actually doing innovation in their infrastructure. Like I gotta say, that's patently false, right? I mean, I've now worked with telcos, I've worked with financials, I've worked with Fortune 100, I've worked with hosting companies, and many of them are actually doing innovation in their network for the purposes of competitive advantage, right? This is not some isolated phenomenon. People actually care. And the reason is because it's the natural extension of what they already do. I mean, they've innovated in their server space, they've innovated in their databases, they've innovated in their storage. Why not the network? Right? And the second one, and I know you guys have been beaten to death with this, but I think it's worth saying, and the second primary value proposition, the first one is a direct benefit. Like if you buy a switch that has OpenFlow, or you buy into the OpenFlow ecosystem, you get the ability to fiddle around with the stuff that you operate. I mean, that's kind of direct benefit, very easy to articulate. The second one is an indirect benefit, and it's less easy to articulate, but I think it kind of gives context to why we should all be in this room and why we should all continue to back this. And that, I mean, it moves the industry towards horizontal integration. And to me, that actually means two things. One, I'm actually not so interested in, which is market efficiency, right? You get competition at every layer. I actually don't really care about that. I mean, I think that's great, but I think it's going to be a long time before we actually realize that. What I do think is very interesting is from a technical perspective, once you decouple layers, they can evolve independently. And I think that means like better products soon, right? I mean, being able to build a system that you can innovate on kind of like software design speeds, right? Like, for example, on the system that I work with, we totally can regress the entire network just from the software layer. We do feature development every 6 weeks, like major new features go out every 6 weeks. I mean, the type of velocity, and I hate that word, but the type of velocity you get for like implementing features and getting them out there on like an actually decoupled system that's not tightly vertically integrated is pretty awesome. I think it's about time that kind of networking kind of hit these types of innovation speeds, because there's an awful lot of work for all of us to do in building new systems, and this is a great way to do it. Okay, so I found people actually aren't very happy with that last answer. They're like, well, okay, but what can I do that I can't do before with OpenFlow? You know? So does OpenFlow offer new functionality? I mean, like, let's be honest. OpenFlow doesn't change chipsets, doesn't change hardware. It's just an interface, right? It's not like it's going to provide you something new. I mean, I was on a call recently, and a guy said, "Wow, I heard that OpenFlow is great for network virtualization." I mean, sure, you can use OpenFlow for network virtualization, right? But like the pioneers in network virtualization don't even use OpenFlow, right? They've got shipping products that have been shipping, and it's like Cisco and VMware that have been shipping for 5 years, right? I mean, OpenFlow is an enabler. It's an open standard. It's useful, but it's not going to enable your hardware to do something that it can't. On the other hand, SDN absolutely allows you to do things that you can't today. Absolutely. Right? I mean, you can just do this from first principles. I mean, I will give you a problem. I'll say, I want to do a policy compiler for a network. You do it purely distributed, I'm going to do it in a tight cluster, and we'll see who builds a better system. In fact, going back to network virtualization, if you look at the products that are in the network virtualization space, they all have SDN-like components. I mean, they have these central systems. They have high-level distributed data source that they use for solving this problem. It's because you have to. I mean, the way that the industry is going to move is going to be in an SDN style. That's the way that you solve these hard problems. That's the way that you manage the complexity of pure distribution. And it's already happening in industry. So what's important for us is to make sure that it happens in a way that's open and that we can contribute and that we build a nice software system. That's really what's important. Okay, does SDN scale? I mean, since the first paper that we wrote, we'd have questions on scale. And I know you guys are probably confused. I just want to do two anecdotes very quickly. So the answer to this is yes, it can scale. Now, the reason that I think that people think it can is because we normally talk about centralization. And like I described it before, there's nothing centralized about it. It's about a different distribution paradigm. You can choose whatever you want. And there's plenty of existence proofs of fully distributed operations that scale to the size of the internet. But I think the second reason there's a lot of confusion about this, which I'm so glad, Dan, that you gave the kind of little snippet that you did this morning, is I think we as a community are totally being sissies about talking about what we've done. I mean, I don't think anybody's sitting there announcing numbers. And like the only numbers I've seen are people like, you go under an NDA and then they'll whisper it to you in the back of a room, right? I mean, I think we should be very proud of building awesome systems. And I'd like to encourage everybody that's building them to like quote numbers. So I'll start. So, I mean, I work on a system that can scale to well over 500 switches and tens of thousands of end hosts under management, and an arbitrary number of flows. I mean, this is a really, really large system. I mean, that's, and the only reason that we haven't tested any further is because we haven't had the need to. And we're not CPU constrained, and we're not memory constrained. I mean, these are big operations. These are bigger than pretty much every fabric I've worked with. I mean, they're huge. And I know of other very large global deployments of OpenFlow out there. So as you guys feel better about that, and you guys get more comfortable, I really encourage you to just kind of stand out and say it. And then a lot of this confusion will go away. Okay, so that all said, I thought I'd take just a couple of moments to think about why we're here, why OpenFlow has been so successful, and what that means about going forward. And the reason I wanted to talk about this is it's been a pretty cool journey, but I want to make sure that we don't kind of lose ourselves as we're going forward and kind of get caught up in the buzz. I mean, there's some real tangible reasons why we've been so successful. And I mean, I've been shocked by how quickly things have taken off, right? I mean, by my account, we have 4 or 5 commercially available switches that support it, probably more. We've got many internal projects that use it. We've got shipping products on the market that use it internally. This is OpenFlow. We've got 3 startups that definitely use it and a handful more that claim to use it. We've got a very, very broad research agenda. But they're not, like, this is tangible success for what started out a fairly small research project to begin with. And so then my question is, why is that? Is that because OpenFlow is some wild new idea? No, clearly not, right? People talked about decoupling the data plane from the control plane for years, right? I mean, this has been standard for years. I think that you can nitpick on issues with that, but it's clearly not that OpenFlow is like some wild new idea. Is it that OpenFlow is well designed? No, like, we totally screwed it up early on. Let me be honest. I mean, like, there were issues that we didn't understand that we understand now. Now we fixed those, and I think that it's moving in a direction that makes it going to be the best competitive technology within the industry for sure. I mean, I think it's going to back, and it's open, which is good, and it's implemented, which is also good. But boy, I mean, early on, the time when it was having this success, it certainly wasn't because it was well designed. Is it because it's a path to new functionality? I mean, SDN's happening. Whether we like it or not, it's happening. Now, we want to make it happen in a certain way so that you build a great community about it. But, you know, OpenFlow isn't going to give you anything new or interesting. So it leaves us with this question of you know, why has it been so successful? And I've been thinking about this an awful lot, you know, as the ONF came up and, you know, being on the tag and watching the success. And I mean, I actually, honestly, very honestly, think the answer is the community, is you. And like, I know how trite that sounds, and I'm not a sappy person, and so I think there's actually a very important message here. And so I want, if you take away anything from my talk, I want you to take away like the next 2 minutes of what I'm going to say. And sorry, like, I wanted to take a picture when it was more full, but you know, I had to transfer it. So that too, like fully populated. So, you know, around kind of a common vision of making networking better through software, we've developed a really broad and diverse community. And it's not just a technical community, right? We have entrepreneurs, we have marketers, we've got project leaders, we've got researchers, we've got, you know, labs guys, we've got management, we've got channels, we've got OEMs, we've got ODMs. I mean, this is a subset of the full networking ecosystem. And I think without that, you kind of have nothing. And I think that's really what differentiates us from any other movement out there. And so I thought about this while I was drafting these slides over the last couple of weeks, and if I look at the major inflection points that have moved OpenFlow to the next level of credibility or adoption or use, it all happened through the broader community and not some like technical standards effort, which is very, very important. But this is the differentiating factor. Let me give you some examples. I'm not sure if Miles or Joe are here, but I mean, really early on, you had 2 administrators in Stanford that had the stones to like deploy like pretty crummy software. We took down gates at least twice, right? Like without the efforts of these guys and the ability to have them run our system in live production, we probably wouldn't have gone as far as we did. If Matt Davies, who is here somewhere, hadn't been such a staunch supporter and kind of pushed OpenFlow on vendors as well as he has and grown such a community, we would never have the type of pickup that we have. If developers like Ben and John hadn't spent all of the time building this open source software and getting it deployed and pushing it out there and getting the support of their organizations to do, I mean, we'd literally be here talking about a pile of papers, right? And it's this kind of broader efforts that really make us what we are. So my capstone sentence is, this is a movement. This isn't the standards committee. It's really a movement, and I really believe that movement lives or dies by the community that's behind it. And I think it's all of our responsibility to cultivate that community. Thank you.
Okay, we have time for some questions. By the way, I forgot to mention that we are recording the session, so if you have any questions for Martin, please do come to the mic and remember that you are being recorded. Okay, so any questions for Martin? No.
Great talk, Martin. Amin Haddad from Google. What do you see as the next milestone for OpenFlow and software-defined networking? How will we know we're on the right path?
It's such a fantastic question. I actually think that is the question, and I don't have a good answer for you, to be honest. I mean, I don't think that there's any new paradigm-shifting hurdle. I think what we need to do is keep doing what we're doing and get this stuff deployed, and then talk about it. Meaning talk about it. I think it's really, Jim, talk about it. I think it's really important that we show these systems working in practice and we talk about when they do. And let's be honest, NEC has been fantastic about this. They've built great systems and they've talked about this. And I think that the next level is for us as a community to work hard, get them deployed and talk about it. I actually don't think there's a lot of technical innovation on it. I think it's a great question. I think it's a very important question.
Any other questions? Oh my God, because I said we are being recorded, people... Come on, you don't get to have my team respond to your questions. Oh, if you don't want to come down, I can pass on the microphone. thought at least someone will ask,
Get to the microphone.
when do you
Can you tell us one thing that you screwed up on in the early design?
Yeah, okay, so the question this question's from Jim from Google, and he asked one thing that we screwed up in the early design, and there's actually many things that we did. So, I mean, one thing I think we got wrong is we're a little bit over-optimistic about what you can do with a single TCAM, right? And so, and listen, you set us straight probably 3 years ago on this, right? Or maybe even longer. We thought that, and Panit also set us straight on this, so we thought that it would be possible to have a data path that was just effectively one TCAM, and you could put all the flows in that TCAM. You'd be really, really clever about encoding those flows using smart software. But the disparity between the lookup power of a TCAM and the management CPU that you could do to use that logic proved to be just too much. And so instead, we evolved the OpenFlow standard to support multiple tables. So I think this is something we just clearly got wrong. Any other questions?
Okay,
Thanks.
thanks again, Martin.